So we are trying to go virtual with this class, and I am trying to use the Khan Academy style videos. And today is our first go at it. So it's taken me a lot longer than I had hoped to get this lecture recorded, but hopefully it'll be a good platform for us as we try to finish out the rest of the semester. All right, so far we've talked about failure, and the failure that we've talked about has been both static failure and dynamic failure. And when we talk about static failure, we are usually talking about the stress is greater than the yield stress for permanent deformation, and the state of stress is greater than the ultimate stress for failure. When we talk about dynamic, we are talking about the fatigue failure, and this is when we looked at all the different fatigue factors and fatigue analysis to see if, to answer the question, do cyclical loads cause failure? And when we looked at these things, one of the things that we really didn't consider is the environment that the mechanical device is actually operating in. It actually turns out to be very important when we talk about surfaces. Okay? And so today we are going to talk about surfaces and surface failures. All right. And of those, so when we talk about surfaces, we're talking about corrosion, cavitation, and wear. Okay, and we'll treat those individually. We'll start off with corrosion. Corrosion is a type of surface damage that occurs due due to chemical and electrochemical mechanisms. Okay, and usually those electrochemical mechanisms have to do with the environment that the surface is placed in. It's estimated that corrosion damage accounts for a pretty considerable amount of cost, and it is greater than 100 billion US dollars. So it's quite a bit of damage that's caused by corrosion per year. And corrosion is a type of surface damage. Sometimes surface damage is also called surface degradation. And it's something that we have to consider when we're doing design, because often we design things that are going to be left in an environment that could be corrosive for many years, and we need to consider what's going to happen to that device. One of the most common forms of corrosion is are excuse me, oxidation, galvanic corrosion. Okay, and we'll look at those individually. All right. Of the two, the most common form is oxidation. And it occurs when we typically talk about oxidation with respect to metals reacting. Sorry, I gotta get used to this tablet here. Metals reacting in air or water. Okay, and we usually have oxygen that's readily present in air and oxygen that's readily present in water. So these are the most common forms, but obviously oxidation can occur when there's oxygen available for the material. Most metals react with air or water, and some metals form oxide layers, and when it forms the oxide layer, it turns out that the oxide layer itself can limit further corrosion, and so these are called self-limiting. So these are self-limiting materials. Okay, as an example, aluminum, which is a very reactive metal, forms an oxide layer that protects it from further oxidation. And this is one of the reasons that you have lots of aluminum marine applications. Okay. The oxide layer for aluminum is around 0.02 microns. And it forms the aluminum oxide. That's the chemical formula for that. Anodizing, which you may have heard of, is a formation of this oxide layer to protect a part. Okay. In contrast, iron alloys form a discontinuous and porous oxide film is iron oxide, which is rust. Now this oxide layer flakes off. It flakes off and exposes more material, which repeats the process of rusting. Okay, so that's why aluminum is commonly used for outdoor applications, because it'll form a protective oxide layer. Contrast iron alloys, they form this discontinuous and porous oxide film that turns into iron oxide, which is rust. So we have some low alloy, steels will create a protective rust colored layer. Which mostly causes galvanic corrosion to stop. There are a number of surface treatment sorry about that. Options for materials to protect surfaces. Okay. So another form of corrosion is galvanic corrosion, and this mechanism is when we essentially have an electrical potential between materials, okay? And in galvanic corrosion, you get current to flow, between materials, and you get ions to disassociate from the base material. Okay, for example, if you have a piece of iron and an electrolyte, you'll get iron ions that will come off the surface of the material. So we have to limit. So from a design perspective, we need to understand how materials will react with each other and limit surface damages by making good decisions on which materials we put together. All right. So we can look at how reactive materials are with each other by taking a look at the galvanic index. Okay. So we can see how reactive materials are. By looking at their galvanic index. All right. So the galvanic index, which is in your book on page 374, tells us how materials, how reactive materials are with each other. And this is the galvanic series. Okay. So if we look over here at the galvanic series for materials, we can see, sorry, bear with me, I'll get this to be less frustrating in the future. Alright, so basically we have materials that are called noble. These materials are materials that are not at all reactive, all the way down to very active materials, and these are lead to corrosion. So these are very, very reactive materials, and these are not very reactive materials. And how reactive a material is can be determined by where it is on this galvanic series. So 1 would be the least reactive, 20 would be the most reactive, and as a rule of thumb, what you want to do is pick materials that are close to one another on this chart. So as an example, we would pick material from this chart that would be close to another material. We can see whether or not they're compatible. And what's interesting to note is if you look at the way the table is separated, if we look here, and we can see okay, so we can look at this and then we can see actually that if we have materials that are far away from each other, there's a area of the graph here where we start to get X's in the material, and we see that they are really not compatible with each other. So materials that are close to each other are compatible. So we see the C's over here, and then below a certain threshold, we see that most of the materials are not compatible, and that's indicated by the number of X's that they have with each other. So if they're close together, they're mostly compatible. If they're not close together, they're mostly not compatible. All right. So that's a basic intro to two types of surface corrosion, and two types of surface damage, which is corrosion and oxidation. So oxidation can actually help us when we're talking about aluminum in some cases. It can actually hurt us when we're talking about iron oxide. And using this table, we can actually take a look at how reactive materials are with one another. And if we look at the table here, we can see that cadmium and aluminum are 3 levels from each other. So using cadmium plated screws in aluminum is likely okay for some environment. But if we put, so we see here is cadmium so we have cadmium. So we have cadmium and aluminum. That's clad aluminum. So we have cadmium and aluminum. So they're the difference between 16 and 19. So they're close to one another. So if we had cadmium coated screws in aluminum, it's probably okay for some environments. But if for some reason somebody put a copper washer between them, then they would cause the aluminum to corrode quite rapidly. So often what's used is in some applications when you have dissimilar materials, is a galvanic union, and these are used to prevent galvanic corrosion. Okay, so plumbers are very well aware of this, and plumbers will use galvanic unions if they have to go through if they have to have a material change between two different materials, and they need to make a seal. So if you go to Home Depot, for example, you can find that they sell these type of devices, which essentially put an insulator between the two different materials so that it'll act as a dielectric break and insulator so that current won't flow, which will prevent the ions from disassociating from the material and causing damage. In your book, there's an example where they have two different plates. Okay. And so the book example 9.1 asks to compare. Okay. I'm really sorry about that. So the book example 9.1 says compare the corrosion in riveted plates. Okay, and they essentially have two plates here, and they are riveted together by a series of screws. I do not know. So we have a series of screws here, or a series of rivets, and the question is if we have a 1 meter squared area for the plate, this would be at 1 meter by 1 meter, and we have 100 centimeters squared from the area of the screws, so the sum of all the areas is equal to 100 centimeters squared. And this plate is exposed to air and possibly some salt. So it's exposed to air and possibly some salt with two L's. So the question is, will it corrode if we have one steel plates with copper rivets, or we have copper plates with steel rivets? Okay, so the purpose of this example and discussion is essentially to just draw your attention to the fact that these are not equal. There's an area effect when it comes to corrosion, and this is a qualitative example, but you should understand qualitatively that we basically, by doing this, we joined two materials. If we go back to our galvanic index, which is now up here. Actually, where did it go? I think we lost it. My apologies. I don't see. There it is. Sorry about that. It disappeared on me. So on one hand we have copper, rivets and steel, and on the other hand we have steel, rivets, and copper. And so you might think that it should be an equal reaction, but it turns out that it's area related. And so the question what they ask you to do is find out, which is worse. So the question is for us is, well, what do you think is worse? Okay, so we have in one case for the steel we have large area of steel and then a small area of copper, and the steel is more active. And in the second case we have a large area of copper and a small area of steel, but the steel is more active. So what's worse? And they also want to know if the metal will corrode, and what is the rate of corrosion, and what happens when we use more rivets. Okay, And so the way to think through this is the steel is more active, and it would cause corrosion in both cases. Okay, because there's 100 times greater current density at the rivet surface than the plate surface due to the area effect. The corrosion rate is the highest if the rivets are steel. Okay, so if we have this very reactive element in a large area of copper, then it actually becomes much more active in this case because there's so much more copper than there is steel, and because the steel is more reactive, then they'll corrode a lot faster. Doubling the amount of steel wouldn't really have much of an effect, but if we used copper rivets instead of steel rivets and we doubled the number of copper rivets, it would double the corrosion rate of the steel plates. And so this is just sort of a qualitative way to think about this. All right, so that is an introduction to surface corrosion and galvanic corrosion and some information about oxidation.